last one I want to evaluate f of 1. So f of 1 means I'm going to plug in 1 for x into the function capital F. So that's going to be the integral from -2 to 1 of f of t dt. And that little f is this function that's here. So if I go from 1 to from -2 to 1, that's going to be from here to here. And so I just need to count up that area. So one thing I can see is that this area and that area are going to add to 0. So I'll have 1 square and a half of a square. So this is 1.5 will be the area of that, because those two areas are gone. And then this area, this is 1, it's square, 1 by 1 square, and this is half of a 1 by 1 square, so it's 1.5. All right, f of -3, let me erase all that. So f of -3 is going to be, I'm going to plug -3 in for x. So integral from -2 to -3 f of t dt. So the first thing you might notice is that it's backwards, right? So it should be negative integral from -3 to -2 f of t dt. Okay, so now I can make sense of that area. So if I go from -3 to -2, that's this area here, and I can see that that again is a square of area 1 plus a triangle of area 1/2. And they're both negative, so I'll have negative of -1.5, which will be positive 1.5. All right, what about f prime of 2? So f prime of 2, of -2 is, well, I know that by the fundamental theorem of calculus part 2, I know that the derivative with respect to x of the integral from -2 to x of f of t dt is going to, so this is capital F prime of x, is the derivative of f of x, which is equal to, by the fundamental theorem part 2, that's f of x. So f prime of -2 is going to be little f of -2, and I can find that value here. I can see little f of -2 is -1. Okay, and f double prime of 2. So if capital F prime is f, then capital F double prime of x is equal to little f prime of x. And if I'm looking for the derivative at 2, the derivative of f at 2, that's the slope here at 2. And that slope is what? Well, the rise is down 2 over 1. So it's -2 over 1, which is -2. So that's the slope when x equal 2. It's the slope of f when x equal 2. Okay, find a value where capital F has a local minimum. Justify your response. So I know that capital F has critical points when capital F prime is equal to 0, but we know capital F prime is equal to little f. Okay, and so the critical points of F are going to be all the places where, the critical points of big F are all the places where little f is equal to 0. So this is a critical point, that's a critical point, and that's a critical point. So if I make a number line here for big F prime of x, my critical points are at -1, 2, and 5. And is capital F positive or negative in between those? So if I'm over here less than -1, little f is below the x-axis, so it has negative values. And then it's positive above the x-axis. And then between 2 and 5, we're below the x-axis, so that's negative. And from 5 to 5 on, it's above the x-axis, so positive. So my function is going down, up. My function is going, whoops, I did it backwards. So my function, when we have negative, it's going down first, then up. Yeah, so my function is going, capital F is going down, then capital F is going up, then down, then up. So if we're looking for a local minimum, that would be here and here would be local minima of capital F. So I could say capital F has local minima at x equal -1 and x equal 5. And this makes sense because what is happening here, I'm accumulating negative area. And then at that point, when I reach -1, I've stopped accumulating negative area and I'm going to start accumulating positive area, which is going to mean my total area is going to increase. And then here, as I go along here, I'll be accumulating again negative area. And then when I get to 5, it's going to stop accumulating negative area. So that's going to be another minimum value of the function capital F.